So infrared spectroscopy, what is the concept here? That when we have the molecule, their bonds are polar, and due to this polarity, they have a tendency to absorb the infrared radiation or IR radiation. Like example, you have say methanol, so which contain CHO and H bond. So because they have a difference in the electronegativity, so these bonds are polar. So when we send these infrared radiation, there's a range for infrared radiation. So when we send these infrared radiation, each bond is having a tendency to absorb a certain amount of or certain range of infrared radiation. So example, we are sending the radiation from zero wave number, zero wave per centimeter, which is called a wave number. How many waves are there every centimeter? That's called a wave number. So from zero wave per centimeter to 3000 or 4000 wave per centimeter. So as a result, what happened? Because different bonds have a different characteristic or tendency to absorb the IR radiation. So example, the CH bond is having a tendency to absorb 1600. This OC bond or CO bond has a tendency to absorb 1900. And this OH bond, it is having example tendency to absorb 3000. So as a result, when we sketch the graph for the wave number on y-axis and the percentage absorption or percentage transmittance, basically percentage transmittance and the wave number, and the scale of this, it is starting with a higher value. Like example, 4000 is there, then 3000 is there, then 2000, then 1000, and then 500, and then 0. So what we'll observe, the one which is absorbed, 1600 is absorbed, 1900 is absorbed, and 3000 is absorbed. So at 3000, which is absorbed, there will be a peak, inverted peak means that is being absorbed. Then there is 900 is being absorbed, so there will be peak at 900, and 1600 is also absorbed, so there will be a peak at 1600. Amount of absorption depends on the type of the bond. Some have a strong absorption, like if the depth of this P, the depth is more, it means strong absorption. If depth is small, it means it is having a weak absorption. So using these number, using the area which the absorption occur, we can identify the number, the type of the bonds present in the molecule. So IR or infrared spectroscopy is mainly used to identify the type of the bond which are present in the molecule. So as you can see, like here it is 4000, 3000, 2000, then 1500. What about the region from 1000 to 0, 1500 to 0? That is called a fingerprint region. Why we call this as a fingerprint region? Because in this region, each molecule is having a distinguished spectrum. So we don't consider this because it is difficult, it is a complex, we cannot read easily because each molecule is having its own unique spectrum, infrared spectrum here. So whenever we determine the number of the bond, the type of, not number of the bond, basically the type of the bond which are present in the molecule, we check the region from 1500 to 4000. And you don't have to memorize these range. In exam, these range will be given. You just have to identify according to the molecule that where it will be the absorption. So as you can see in this one, this is the range which is absorbed, and this is the second one. So two absorptions are there. So we'll check a region. So this is the absorption from 3300 to 2500. So that correspond to OH. Like this correspond that there is a OH bond or HO bond. And another peak, a sharp peak is there from 1750 to 1640. So this sharp peak is because of OC or CO. So it means this molecule contain C double bonded with O and it contain OH. So what we can identify, we can say that this molecule can be a carboxylic acid because carboxylic acid contains C double bonded with O and it also contain OH. So using the bond, we can predict the functional group present in the molecule. Is it clear the concept of infrared spectroscopy? So IR or infrared spectroscopy is mainly used to identify the type of the bonds which are present. So as you can see here, there's a table on the left hand side. Again, I repeat, you don't have to memorize these values. It will be given like here OC bond, it is absorption from 1000 to 1300. C double bonded with O 1640 to 1750. CH bond is there, OH bond, NH bond, and OH bond of alcohol and phenol. Phenol means like when the benzene, there's a benzene ring. In A2, you will study when benzene ring is attached with OH, we call that as a phenol. Now, example, we have a molecule such as butanol. So we have a butanol. So how to identify, how to confirm that it is a butanol? So there should be C double bonded with O peak should be there. And that peak C double bonded with O peak is how, what range? It is from 1640 to 1750. And you can see the range is small. So range is small. This is a small range. And when you check the region, because this is 1500, 1600, 1700 and 1800. And each is representing like because 1550, 1600 and 1000 about 700. This is 2000, so 1 2 3 4. Okay, so each is representing 100 only, 1600, 1700, 1800. So it is a peak is there around 1750 because any peak within this range correspond to C double bonded with O. So this peak correspond to C double bonded with O. And there's another region is there for 3000. So when you check, because whenever CH bonds are there, the other type of bond which are present, that is the CH bond. So when I draw the structure, the displayed formula represent all the bonds which are present. So these are all the bonds which are present. So they, if it's in butanol, 4 carbon atoms are there. So where we'll get a peak, we should get a peak for C double bonded with O, and we should get a peak for CH. So CH should be there, means from 2850 to 3100. So this is a region, that means this is representing a CH peak, and there is C double bonded with O peak as well. So this confirmed that this spectrum is for butanol. Another example, say you have ethanoic acid. So if you have ethanoic acid, so instead of determine the, because mostly contain carbon and hydrogen, so we don't use carbon and hydrogen to distinguish whether it is an alcohol or carboxylic acid or aldehyde or ketone. We normally use the functional group peaks to distinguish. So if we have ethanol, which is C double bonded with ONH, so CH peak is always there. Now, what can happen? There can be C double bonded with O peak can be there, or there can be OH peak, or CO peak can also be there. So when we check the range here, there is a broad spectrum, a broad absorption in this region. and there is a sharp absorption in the other part. So this absorption refers to what? It refers that there is C double bonded with O, and this absorption refers that is OH. So one confirms there is OH, another shows that there is C double bonded with O. So this is the infrared spectrum of ethanoic acid. So it, even if it was butanoic acid, same will be there. Pentanoic acid, same, because the type of the acid, which acid is there, that we can not determine from this region. We only determine the type of the bond present. The only difference between ethanoic acid, the spectrum of ethanoic acid with methanoic acid with butanoic acid, is the fingerprint region. But fingerprint region, it is a complex to read this whole part. There are a lot of peaks. That's why we don't use it. We will use only the part where we can determine the bonds present in the molecule. So even if it is a spectrum for butanol, butanoic acid, pentanoic acid, or methanoic acid, they all have the same result. So the molecule which change their polarity can vibrate, they can leads to absorption of infrared, but there are molecules which, like molecules such as H2, O2 or N2, cannot change their polarity because they're identical atoms are there, they have the same electronegativity, so they don't have poles on them. That's why they cannot absorb these infrared radiation. So they cannot change their polarity as they vibrate. So they can absorb, but they do not register any infrared spectrum. Their absorption can happen, but they cannot leads to emission of any infrared radiation. So absorption of infrared radiation by bonds depends on, like example, the difference in the polarity. So absorption of the infrared radiation by bonds in this type of spectroscopy is same as absorption of the bonds in like CO or methane, CH4 or water, which cause a global warming, and these are the greenhouse gases. So H2, CO2, CH4, NO molecules, they have the tendency to absorb infrared radiation and are known as the greenhouse gases. Is it clear how infrared spectrum or infrared spectroscopy can be used to determine the type of the bonds which are present in the molecule? Any doubt till this point? So this is basically a flow chart to show how the organic chemistry reaction can occur. So yes, mechanisms are there. Like example, you have alkene. If you want to convert alkene into polyalkene, you want to make an addition polymer. So what are the conditions? You should use a high pressure catalyst, and this process is called polymerization. If you have alkene and you want to convert dihalogenalkane, like we want to undergo addition reaction, such as adding chlorine or bromine at a room temperature, but what kind of what will be the type? It will be electrophilic, like the type of the reaction electrophilic, and the mechanism, it will be addition. So electrophilic addition reaction will occur. But if alkene is there, we want to convert into diol. So what we can do, we can use potassium KMNO4. The reaction is known as oxidation reaction. Same thing if we have alkene and we want to convert into alkane. So we use nickel as a catalyst, and this reaction is known as addition, or we can say reduction, because in which hydrogen is added. Whenever addition of hydrogen is also refers to reduction, it gives alkane. Or alkene is there, we use hydrogen bromide or hydrogen chloride at room temperature. Again, electrophilic addition reaction will take place and it will form halogenoalkane. Or alkane is there, we can use UV ultraviolet radiation. It will undergo free radical substitution reaction and it will result in a formation of halogenalkane. Or halogen alkane, if we have halogen alkane, we discussed in unit 2 that if halogen alkane, if we undergo like in aqua, if we have alcoholic potassium hydroxide and we heat under reflux, it will undergo elimination reaction and form an alkene back. And if halogen alkane reacted with ammonia, that it result in a formation of amine, the reaction is nucleophilic substitution. Halogenoalkane can be converted into alcohol by reacting with aqueous potassium hydroxide, or alcohol can be converted into halogenoalkane by reacting with either PCl5 or PBr3 or PI3 when we heat under reflux, and the reaction is substitution reaction. The alcohol, then we can do oxidation of alcohol depending on the type of alcohol. If it's a primary alcohol, it will be oxidized to aldehyde. Secondary alcohol oxidized to ketone, and further oxidation of aldehyde leads to carboxylic acid. So this is all, like, this is the summary of all the organic chemistry reaction which we have discussed throughout unit 1 and unit 2. So it's important that you know or understand this, that how one of the reagent can be converted into the desired product. Then just a quick overview of how the reaction can occur. Like we can have substitution reaction. So introduction to mechanism, like how reaction can occur. Whenever first the bond break, either it can be a homolytic bond breaking or a heterolytic bond breaking. Homolytic bond breaking, it produce free radicals, means atom with a one electron on them, we call that as free radical. So, and whenever we represent a homolytic bond breaking, so we represent by a half arrow, or it is also known as homolytic fission, and it result in a formation of a free radical. Free radical do not have any charge and they are represented by dot. Like example, if I say I have CH3 and then CH3, and they break down, the molecule break down, it produces free radical. So I'll draw a half arrow, not the full arrow. Half arrow means one electron, because in a bonding there are two electrons, one is taken by one of the CH3, other one by the second CH3. So this is called homolytic bond breaking. In heterolytic bond breaking, the electrons, the pair of electron which is shared, both electrons are taken by one of the element. The element which take those electron will get a negative, the other one will be positive. And it can be happen other way around, like X is reacting with Y. So if Y is taking both of the electron, Y will be negative and X will be positive. So free radical is a reactive species which possess an unpaired electron, and heterolytic result in a formation of ions. Then mechanism here refers to how the reaction proceed. We call that as a mechanism. And whenever we draw the arrow, the direction of the arrow is the movement of basically the electrons, how the electrons are moving. Like as you can see here, carbon is bonded with halogen. Halogen is more electronegative, so halogen will take both of the electrons, and oxygen supply the electron to the carbon to try to form with carbon. So mechanism can be addition. The reaction can be addition reaction. Addition means when two or more molecules combine and they give one product, we call addition. Substitution means like swapping of the one molecule by the other atom or group of atom, we call substitution. Electrophile means their electron pair acceptor or electron loving group. So electron loving group, normally they have a positive charge. And what are nucleophile? Nucleophile means nucleus loving group or their electron pair donors. They should have a lone pair. So there should be a lone pair for the nucleophile. And definition of a free radical, that it's a reactive species which possess an unpaired electron. An addition reaction, like, so when we have the type of a reaction which we have discussed here, it can be a substitution reaction. So you have to learn the mechanism. Number one, the mechanism which you have to learn. There is a free radical substitution reaction in alkane. That is one thing. The second, electrophilic addition reaction in alkene. That mechanism you have to learn. The third one is a nucleophilic substitution reaction in halogenoalkanes. The mechanism you have to learn this. And the last one is elimination reaction in halogenoalkanes. So these are the mechanism which you have to learn. The free radical substitution, this is in unit 1. These two are the unit 1 mechanisms, and the other two are the unit 2 mechanisms. So example, reaction of alkene with bromine. So what kind of reaction is this? This is called electrophilic addition reaction. So electrophiles are attracted towards their electron acceptor. They have the tendency to accept the electron. So what will happen in this case? Alkene will convert into dihalogenalkane. It can occur when alkene react with hydrogen bromide. The reactions of alkene, when all the addition reaction of alkene are electrophilic addition reaction. So example, we have ethene reacting with bromine. So ethene, carbon-carbon double bond, but bromine, because two bromine atoms, they have a same tendency to attract the electron. So they will be non-polar. But when they come closer to the double bond, because the double bond, it's an electron rich side, so this double bond repel the bond within the bromine. So the side which is facing a double bond, that will be partial positive, and the other side of a bromine will be partial negative, as you can see here. Then how to draw arrow? Direction of the arrow is always important. So draw the arrow from double bond of alkene to one of the bromine, which is partial positive, and the second arrow, the bond between the bromine to the bromide, which is partial negative. So this will take the electron, and when it will take the electron, this will be bromide ion, and one of the bromine will form a bond. When one bromine forms a bond here, this will be one of the carbon, because there are two bonds, double bond is there, out of double, one of the bond break, and these electrons are forming a bond with bromine. So one of the carbon, either on the left hand side or right hand side, can be carbon cation. And carbon cation, which is surrounded by more alkyl groups, are more stable, because these alkyl groups, they tend to release the electron. They don't have, like electron donating groups, they reduce the positive charge on the cation. So this partial positive ion attract the lone pair of a bromide ion, the second, and it undergo double, like addition reaction is there, and it produce 1,2-dibromo ethane. And remember, this is valid for all. Like example, this is how the mechanism occur for all the alkenes. It is independent of what alkene is there. This always, whenever we draw the arrows, we should always draw the arrow. Like if I say I have propene, so prop means 3 carbon, C double bonded with C, and then CH3. This will be H, and this will be H2. Now what happened when there's a bromine molecule? The part which is closer to a double bond will be partial positive, and opposite will be partial negative. So when we draw one of the arrow from double bond to the one of the partial positive bromine, and the second one, this will break the bond. Now as it will break the bond, then two possibilities are there, because because the bond is break between these first and second carbon. So first carbon can be complete positive, or second can be complete positive. So if it is CH2, if this is positive, CH and Br and CH3. And what is the second possibility? That CH2, Br, the central one is partial positive, completely positive, and then CH3. So when we check which is more stable carbon cation, so as you can see, this carbon cation is surrounded by only one carbon chain. So carbon cation surrounded by one carbon chain. The other one, the carbon cation is surrounded by two carbon chains. It means the one which is surrounded by more carbon chain, that is more stable. And the other one, the top one, is less stable. So which one likely to form? Majority of the molecule will break down in the second option as compared to the first one. And then what happened? The bromide ion, which already took those electrons, which is having lone pairs and a negative charge, this bromide ion will form a bond with CH and it will complete the structure. So this is always what happened in electrophilic addition reaction in alkenes. And same way, if hydrogen halide like HCl or HBr is added, so as a result, what will happen? You can see the double bond, we draw arrow, curly arrow from double bond to the partial positive, and bromine will break the bond. Hydrogen is attached either on the left or the right, because this is a symmetrical alkene, so it does not make difference. And then the bromide will complete and draw the structure. So it is always same, it will not make any difference. Is it clear how electrophilic addition reaction can occur in alkenes? Then the next is nucleophilic substitution reaction. So nucleophilic substitution reaction, like that in halogen SN reaction, and it can be SN2 or it can be SN1. So in a nucleophilic substitution reaction, it occur in aqueous potassium hydroxide, and the halogens will convert into alcohol. How this reaction will occur? And it also depends on the type of halogen alkane. If it is a primary halogen alkane, then it will undergo SN2 reaction. And if it is tertiary halogen alkane, then it result in a formation of SN1 reaction. So what happened? Drawing the arrows, again, it is very important thing to draw arrow correctly. So all, and writing the polarity. So in this case, because carbon is less electronegative than halogen, so carbon will always be partial positive and the bromide will be partial negative. Then the attacking nucleophile, because the nucleophilic substitution, one atom or group of atom will enter and the other will leave. So the OH is the attacking nucleophile. It will attack on the positive sensor. So always draw the arrow from the lone pair of OH to the carbon. And then bromine will take both of the electrons. So as a result, what happened? Bond breaking and bond forming will take place at the same time. And the charge which will appear on the transition state intermediate, that is negative. Why negative? Because overall this molecule is neutral originally, but OH is having a negative charge. That's why the molecule, the whole transition state will be negative. And then Br will break the bond and OH is forming the bond. As a result, the bromide ion will leave and it will form an alcohol. This happened with the primary halogen alkane. Tertiary halogen alkane, because of steric hindrance, as you can see, this is a tertiary halogen alkane. So carbon which is bonded with halogen is surrounded by more alkyl groups, so OH does not find a space to attack on this. So as a result, first what happened, the bond between the carbon and the bromine break. So now carbon cation is formed, and now this carbon cation can attract the OH and it result in a formation of alcohol. So here the intermediate carbon cation positive is formed, the other one it was a negative ion. Here the bond breaking and bond forming take place at the same time, whereas first in tertiary, the bond will break and then this bond will form. So SN2, S means substitution, N means nucleophilic, and 2 stands for that the rate or speed of reaction depends on two molecules. Whereas SN1, S means substitution, N means nucleophilic, and the rate depends on only one molecule. So same idea is that if nucleophilic substitution reaction of halogen alkane with ammonia, the attacking nucleophile is NH3, which is having a lone pair, bromine, break the bond. But this additional extra thing is there, that because nitrogen can form maximum 3 bonds when it belongs to group 5, but here nitrogen is forming 4 bonds. How nitrogen is forming 4 bonds? Because the nitrogen donate electrons. So when it donate electron, now it's having 4, and there will be a charge of +1. So charge of +1, 4 electrons, that's why it can form 4 bonds here. But it is not stable, so another molecule of ammonia attract this hydrogen, and nitrogen take the electron from hydrogen, so the compound will become stable. And further substitution, basically what happened, so this reaction, the formation of this product depends on the presence of NH3. If we have a limited supply of NH3, then multiple substitution will occur until all of the hydrogen of nitrogen are replaced by alkyl group. If we have excess of ammonia, then we will get amine as well as ammonium bromide. So the free radical substitution reaction which occur in which occur in alkanes, due to ultraviolet light, first the homolytic bond breaking will occur, which produce a free radical, and that free radical can attack on the halogen. So when it attack on the halogen, it will form HCl and methyl radical, and methyl radical react with another chlorine molecule, form methyl chloride and chlorine radical. So this is called a propagation step, in which the same chloride radical produce again and again. So the cycle continue. How the reaction terminate or stop? When radicals are stop, means when the radicals form a bond with each other, then the reaction only stops. So if methyl radical react with another methyl radical, it will form ethane, and CH3 react with Cl, methyl chloride and chlorine react with another chlorine radical, form chlorine molecule. So the termination step, how the reaction can stop, it is by removing all the free radicals. And same thing is there for bromine substitution. The ozone layer, the layer of the atmosphere which is not allowing the harmful UV or ultraviolet radiation to enter the Earth's atmosphere, and how it is able to block that. Basically, two things are there. On the upper atmosphere, there is a formation of a ozone and there is depletion of ozone. That's how it is stopped. Like example, when ultraviolet radiation falls on oxygen, it will produce oxygen atoms. And as a result of formation of this oxygen atom, it combined with another molecule and it forms O3, ozone. And what is the structure of ozone? So there is a dative bonding here, because oxygen belongs to group 6. So each oxygen share 2 electrons. So this is the structure of oxygen molecule, and 4 unpaired electrons are there. But if there is another oxygen atom which is having 6 electrons, so how it can gain stability? By forming a dative bond. So this both electron pairs are donated by one of the oxygen. So as a result, what happened? It will form a dative bonding. So in ozone, we have a covalent bond between the two atoms, two oxygen atom, and then there is a dative bond with the second and the third oxygen. So how the ozone is protecting the earth from the harmful ultraviolet radiation? Like example, this is our earth. So the upper atmosphere, we have, this is formation of ozone. How ozone is formed? Like due to, for oxygen is there in the atmosphere, so this oxygen due to UV light or ultraviolet light, bond breaking occur, homolytic bond breaking, it form oxygen atom, and these oxygen atoms combine with another oxygen molecule to form ozone. So this ozone is formed due to reaction between oxygen atom which are produced due to UV light or ultraviolet light, and this is how ozone is formed, formation of ozone. And how depletion of ozone is there, how ozone deplete this ozone which is formed ozone molecule. So due to ultraviolet light it can also break down, so ozone can form due to ultraviolet light, and ozone also break down into oxygen molecule and oxygen atom due to ultraviolet light. So both cases it is absorbing the UV, and that's how it is protecting the earth's surface from these ultraviolet radiation to enter the earth's atmosphere. But as we are using chlorofluorocarbons, CFCs, they cause a ozone depletion. Like we, or oxides of nitrogen are also causing a depletion of ozone. So what happened when you are using CFCs, chlorofluorocarbons? So the bond break between the carbon and the chlorine, and it produces a chlorine free radical. So this chlorine free radical react with ozone, and it will form chlorate radical and oxygen, and this chlorate radical react with oxygen radical in the atmosphere, form oxygen and chloride ion, sorry, chlorine radical. So what happened overall, it's like oxygen chloride, this chlorine radical is acting like a catalyst, like it cause a breaking down of ozone, and that is why there's a depletion of ozone. Same thing happened with the oxides of nitrogen. As the aircraft, uh, as they're flying at a higher altitude, so nitrogen and oxygen from the air react with each other and produce oxides of nitrogen such as nitrogen monoxide or nitrogen dioxide. And this nitrogen monoxide also reacted with ozone and it formed oxygen gas. So as a result, what happened? There will be a depletion of ozone. So ozone is forming, ozone is depleting as well, but because of the human activities, as we are using these refrigerant gas, chlorofluorocarbons, so due to the use of CFCs, this result in a formation of another depleter, ozone depleter. Now these CFCs, chlorofluorocarbons, are replaced by HCFCs, which are hydrofluorocarbons, which does not have chlorine bond, so it cannot cause ozone depletion. So CFCs and oxides of nitrogen cause a depletion of ozone. So this was about the analysis and mechanism. That was the last topic of unit 2. Any question or a doubt?